Hi students, welcome to Max Point of View. Today we are going to understand the concept of force on current carrying conductor in a magnetic field and its application of DC motor. This is part B of magnetic effect of electric current chapter. So this is a concept video. After this we are going to solve each and every theory question which is there in your textbook so that you will get complete knowledge about this chapter. See, when it comes to electromagnetism, logical and application questions are very easy to create for the people who are creating the paper. So for us, we have to gain the complete knowledge. It is not like other chapters where you can get some numericals, all those things. In this electromagnetism, numericals are very rare. So understand the concept properly. So previous year papers, all those things are very much important, mainly for this chapter. So after solving all the concept videos, theory solution as well as numerical, we are going to solve previous year paper solution, not only teaching you or providing you the solution, we are going to train you so that for the same question, what if they ask a question in a different angle. All those things are very much important. After that, logical plus application oriented question. All these videos are chapter wise. From the electromagnetism chapter, what are the previous year questions, what are the logical and expected questions, all those things we are going to do chapter wise. All these videos are available in the description box. So without wasting any time, we'll start with our concept. Whenever a magnet, that is normal magnet, and a current carrying conductor brought near to each other, a force will be generated. This was observed by Lorentz. So these kind of forces are called Lorentz forces. So this is called as Lorentz force. See, I'll repeat one more time. When a magnet, a normal magnet, and a current carrying conductor are brought near to each other, but not in the same direction. Keep this in mind. See, if the current direction is here in this direction and the magnetic field direction is also in the same direction, no force will be generated. Actually, force will be generated, but from the current. See, this is magnetic field. Okay, from the current, one force will be generated, that is magnetic force, and because of the normal magnet, a magnetic force will be there. Those two will get cancel each other, so net force will be zero. That's why now the magnet and the current should not be in the same direction or should not be parallel to each other. Then no force, net force will be zero. So whenever we have to keep a magnet and a conductor, a current carrying conductor, it should not be in the same direction in any direction except in the same direction. In any direction, it generates a force. That force is called as Lorentz force. Based on that only we are going to learning a concept by understanding this experiment. Listen, see, first we'll understand the setup. This is just a stand. Okay, this is just a stand. See, here the important things are, we know battery, we know the purpose of battery. See, whenever this is just a cell. Okay, if you add one more cell, that becomes a battery. Keep this in mind. The combination of two or more cells are called battery. There is no rule that we have to add only two. You can add as much as you want. That depends upon the voltage required for the setup. So more than a cell, it is called battery. And we know the function of rheostat. See, when it comes to these kind of setups, rheostat plays an important role. Okay, here we are going to increase or reduce the value of resistance. Based on the value of resistance, current value will be changed. If you increase the resistance value, current value will decrease, because those two are inversely proportional. This is a basic concept, correct? So that is very much important. Based on that only the force generated, all those things will be varied. That's why rheostat is very much important. So, and we know the switch, key switch, right? If there is no dot inside that means this is an open circuit. If you have a dot inside, that means it is a closed circuit. In the closed circuit, current can easily pass. Okay, in which direction current is passing? In this direction, right? But we don't care about this direction. We care only about the direction in a conductor. See, this AC is a thick conductor. This AC is a thick conductor. So, and we have a magnet, okay, normal magnet which has U-shaped magnet, okay, which has north and south. So when it comes to magnet, the direction of magnetic field is very much important. We know always outside the magnet, this magnetic field line will start moving from north to south, correct? Keep this in mind, magnetic field always start moving from north to south. That is very much important. That is the direction. And when it comes to a conductor, current direction is very much important, but all these directions are not important. Where is the conductor? Which conductor we are talking about? The conductor AC, correct? Here the direction of current, this direction is very much important. This is towards right, okay, and this direction of magnetic field will be from north to south. All these things are very much important, so don't worry about this arrow mark, okay. Instead, if I don't put this arrow mark, if I connect this one to the this terminal of the rheostat, it will become a resistance, correct? So how to differentiate between resistance and a rheostat? If you connect this one, here somewhere here it becomes a resistor. Resistor is a fixed value, okay. Rheostat, we can change the value of resistance. So whenever we are writing the rheostat, this arrow mark is very much important. Now once we understand the setup, okay, we will directly go into the topic. Now when there is no current is flowing, okay, this conductor will not move to or fro, okay, it will be still. But when the current is passed, okay, from the positive terminal, here from the positive terminal it goes here and current is flowing towards right side, and we know magnetic field will be always from north to south. Now how to find the direction of force? Okay, I told you, whenever there is a current carrying conductor and a magnetic field, okay, magnetic field, extra normal magnet is there, a force will be generated. That is nothing but Lorentz force. Now it is important for us to find the direction of that particular force. That is nothing but Lorentz force. How to find that? Using the rule. What rule is that? Fleming's left hand rule. But which hand I am using? This is a right hand. You should not use a right hand. It's a Fleming's left hand rule, so you have to use left hand only. So few students, even though they know the concept, in the exam, instead of using left hand, they'll use right hand. That mistakes, if you do during the exam, complete 3 to 4 marks will be deducted. See, based on this concept, Lorentz force, pakka one question will be there in the board exam, that is for 3 to 4 marks. And few students, they don't know the concept of how to find the force direction, all those things. That's why they are going to skip that question, even though remaining 2 questions are easy. And this question, these kind of questions will not be in part A, it will be in part B. Okay, you have a choice. But if you know this concept, believe me, within 1 minute you will get 3 to 4 marks if you know this concept. How to use Fleming's left hand rule? If you know the concept, aramse you can get that. And believe me, below this question, the remaining 2 questions will be very easy. Okay, if this question is made tough, remaining 2 questions will be very easy. Only because of this question, many students will skip this question in the board exam. Okay, now we'll understand this one. When the current is passed, see, the direction of current here, anywhere here is not important. It is in the conductor. This is the conductor, right? AC is the conductor. In the conductor, the direction of current, it is towards right side. So whenever we have to use Fleming's left hand rule, first we need to know what are these fingers representing. See, Fleming's left hand rule is nothing but when you stretch a thumb, forefinger and middle finger of your left hand, they are which should be mutually perpendicular to each other. See, this thumb and forefinger are perpendicular, correct? And this forefinger and middle finger are perpendicular. You have to hold it like this. All of them are mutually perpendicular to each other. Once you find that, which represents what, that is very much important. The thumb represents the direction of force generated. So we know force is going to generated in which direction, that is what we are going to get from this thumb. Okay, next, this forefinger represents magnetic field. Forefinger represents magnetic field, direction of magnetic field, and this middle finger represents the direction of current. So how to remember all these things in a simple way? FBI, F force, B represents magnetic field when it comes to electromagnetism, that to physics. Okay, in physics, B represents, capital B represents magnetic field. Keep this in mind. I, we know that is current. F, B, I. Once we know all these things, we can easily use this one. See, once we use it, you see how much time it will take. Now listen, first always assign the direction of magnetic field. Keep this in mind. Once we got to know, we have to use Fleming's left hand rule. Okay, you have to assign the direction of magnetic field first, then everything will be easy. So this is the direction of magnetic field, correct? And we know the magnetic field always move from north to south. So see, this, the forefinger represents what? Magnetic field. You keep it like that. Okay, you can keep it in any way. Okay, then once you keep it like this, next thing is direction of current. Direction of current is towards right. So I'm keeping this, keeping my hand towards right. See, once you keep it like this, see, very much important. First assign the direction of magnetic field. See, this is the magnetic field. I'm going to assign it like exactly in the picture. Next, I'm going to see, sometimes, see, for this question, okay, for now, for the present situation, my for middle finger is automatically arranged towards the direction of current. So it is okay. I'm going to teach you, if we, what if we reverse the direction of current also, then you will understand. Now see the direction of thumb. It is, see, if I stand here, thumb is towards the observer, correct? Towards the observer. So this metallic conductor will move towards the observer. That means force is towards the observer. You understood? See, I'll repeat one more time. First we have to assign the forefinger. Always assign the forefinger in the direction of magnetic field. See, magnetic field is always flowing from north to south. Now I'll keep it like this. Okay, now, so my middle finger is automatically arranged according to the direction of current. For only for this situation, we have many situations. I will teach it now only. Don't worry about it. Now, once you assign both, see the direction of force. It is towards me, correct? I am the observer. If you stand here, the force is towards me. So this metallic conductor will be moved towards me. So the force will be created. So on the metallic conductor, always force is created on the metallic conductor, where it is moving, whether it is moving back side or moving forward or left side or right side. All those things are very much important. So now according to the diagram, the force is towards the observer. So this metallic conductor will move towards the observer. So force is towards the observer. That is nothing but the metallic conductor will move towards the observer. See, for any diagram like this, there is no rule that force should be always towards the observer. It depends upon many things: direction of current and direction of magnetic field. If any one is reversed, okay, the force will also be reversed. Okay, now we'll do that also. Now what happens after reversing the direction of current? We'll change the direction of current. Now see, if you change the direction of current, okay, assume I'm not going to do any changes here. I'm just going to do this change. This is not correct. The long line should be on that side, then it will become positive, correct? So just for an experiment here, I'm changing the direction of current. Okay, now when the current is flowing from this direction, okay, assume the current is flowing from this direction. Don't worry about the polarities of the battery. Assume the direction is like this. Okay, now we have to assign our fingers. See, first always assign what? The magnetic field line. Now we know the magnetic field lines, okay, are moving from north to south. If you hold it like this, this is wrong. Why? Because see the direction of current, this middle finger that shows the direction of current, but the direction of current is towards left side, correct? So you have to change it. See, now see, this forefinger represents the direction of magnetic field. That is correct. This middle finger is towards the left side. This is also correct. See the direction of force. It is towards the board. That is nothing but away from the observer. If you are standing here, okay, if you hold it like this properly, assigning the fingers are very much important. Then the force will be towards the board. If the observer is here, the metallic conductor will move away from him. After reversing the direction of current, the force direction will also be reversed. What if we change the direction of magnetic field? MF represents magnetic field. In the exam, if you write MF or any short form, not only for this word, for any word, if you use any short form, they are going to deduct marks. So never ever use short form. Now listen, on reversing the direction of magnetic field, what happens? So assume for we'll go for initial case only. Okay, the current is flowing from this direction. We are going to change the direction of magnetic field. North is here, south is here. North is here, south is here. Now we'll see what happens to the force. Okay, now see first always we have to assign the direction, the forefinger, correct? We have to assign the direction for forefinger. See here, this is the correct direction, because we know always the magnetic field flows from north to south, and we have to use left hand rule. Keep this in mind. Now listen, so first I'll assign the forefinger value. See, it is in the direction, okay, towards south. Okay, next, the direction of current is towards me. Do you think that is correct? It has to be towards right, so you have to change it accordingly. See, now this forefinger is towards yes, that is correct. Okay, direction of magnetic field is correct. Now the middle finger is facing towards right. Now the direction of current is correct. Now see the thumb. Where is the thumb? Thumb is towards the board. That means if the observer is here, if the thumb, the force direction is away from the observer, correct? In the first case, when the current is flowing from in the same direction, when the south was here, north was here. Okay, exact opposite. The force was towards the observer. Now for the present case, it is away from the observer. This is what happens. So this is how you have to use Fleming's left hand rule. Understood? So this, once you know this one, very simple. In 2025 paper also, this question was asked in board exam for 4 marks. Very simple way. Whether this will move in which direction, whether it moves towards this or to away from this, all those simple questions only. If you know how to apply Fleming's left hand rule, you can aramse answer any question. Now on reversing the direction of current, also force reverses. Keep this in mind. What force is that? Lorentz force, because he found it. Okay, then on reversing the direction of magnetic field, also force, the direction of force reverses. Next we'll go for expression based on this experiment. So there is an equation. So how force is created, we know, right? Okay, how much force is created, how to identify? That depends upon how much current is there, and strength of magnetic field. See, remember this one, B represents magnetic field. Keep this in mind. So B represents magnetic field. See, that is nothing but magnetic field of this U-shaped magnet. That is nothing but B. Then L, length of the conductor. Force, okay, whatever the force is generated, that is directly proportional to current, that is directly proportional to magnetic field, that is directly proportional to length of the conductor. Now listen, how the force generated is related to length of the conductor, directly proportional. How that is related to magnetic field, that is also directly proportional. What do you mean by directly proportional? That means if current increases, force will also increases. If magnetic field increases, force will also be increases. If the length of the conductor increases, force generated will also increase. This is the expression. This is very important expression. When if any question is asked based on these 3 things, force, magnetic field and current, this is the expression you have to write. Expression means formula. This is the formula you have to write first. This formula should come to your mind. Force, current and magnetic field. This is the only formula. Now unit of B. This is one question you can expect. So what is the unit of B here? Okay. See, what is B? Magnetic field. So if we want to find the unit of B, see B, send everything that side. Send everything that side, because see, we know the unit of F. What is F? Force. Force unit is Newton. Aramse we can say directly, correct? When it comes to current, we know the unit, that is ampere. When it comes to length of the conductor, it is meter. All of them we know except B, correct? That's why we are finding that. Okay, see, they will not ask you what is the unit of I, F or L. They will ask you only B because it is difficult, it is not direct. If you want B, send everything that side. So F divided by I into L is equal to B. Correct. I can write this one as B is equal to F divided by I into L. Now, so what is the unit of force? Newton. What is the unit of current? Ampere. What is the unit of length? That is meter. So it is Newton per ampere per meter. This is the unit. See, whenever these kind of questions, there is one question related to this one. Okay, in a theory solution, there we are going to do all these things, but in the exam you don't have to do all these things. This is enough. If you write this answer directly without doing all these things, you will get full mark, because this question will be based on only for 1 mark. Okay, if they ask you to derive, then these kind of things will help you. Whenever they ask for unit, you don't have to do all these circles. If you know the answer directly, you can write this answer directly, or else you can follow this method. We have used Fleming's left hand rule in an experiment, but we have to learn how to define it also. Correct. See, when it comes to Fleming's left hand rule, why we are using this, that is very much important. Why we are using Fleming's left hand rule? To find what? The direction of force. Correct. Keep this in mind. Why we are using Fleming's left hand rule? To find the direction of force generated. When force will be generated? When magnet is brought near to the current carrying conductor. If the magnetic field lines direction and the current direction is in the same direction, both are parallel to each other or in the same direction, no force will be generated. No force will be generated. It in any direction force generates. But when it comes to perpendicular, when the angle between the magnetic field and the direction of current is 90 degree, then the maximum force will be generated. If the angle between them are 0, if they are parallel, that means the angle between them are 0, then the force will also be 0. So all these things, in any direction the force will be generated. But when these two are normal, okay, magnetic field lines and this direction of current are normal, or you can use it as perpendicular. Okay, when these two are normal or perpendicular, maximum force will be generated. This is very much important. Now we'll try to define Fleming's left hand rule. Now listen, stretch your thumb, forefinger and middle finger of your left hand. Left hand is very much important. So once you stretch it, all of these 3 fingers should be mutually perpendicular to each other. See, the thumb should be perpendicular to the forefinger and the forefinger should be perpendicular to the middle finger. Then this is correct orientation. Once you hold it like this, then the thumb represents the direction of force generated, the forefinger represents the direction of magnetic field, and this middle finger represents direction of current. How to remember this in a easier way? F, B, I. This is what we have learnt. F force, B represents magnetic field, I represents current. So F, B, I in an order you can easily remember. This is how you can define Fleming's left hand rule. Okay. Now we'll talk about DC motor. See, when it comes to DC motor, many students will think the working and all, it's really confusing. So the good news is the working is not there in the syllabus. Working is not there. Just the diagram. They may ask for 3 to 4 marks. One thing. Next, the parts and their functions are very much important. And one very simple thing. Whether this coil will flow anti-clockwise direction or clockwise direction. That means you know everything about the DC motor which is there in the syllabus. That's it. We know, see here we are providing electricity. This is battery. Whenever you see battery, that means we are giving electricity. Okay. Next, there is a magnet. Correct. We are providing electricity. There is a magnet. So in presence of electricity and magnet, a force will be generated. Because of that force, this coil is going to rotate. So that means we are going to have to use Fleming's left hand rule. Now we got this much idea. Now we are going to learn one by one. First we'll understand the diagram. See, north and south of the magnets are very much important. Keep this in mind. Okay, in some, see the same diagram in theory solutions also, the same, everything is same. Okay, the working is also same. And in this diagram, we are going to get anti-clockwise. In some other diagram, it will be clockwise. The same diagram, the students will be confused. Why? Because here in this diagram, the position of north and south is north is on the left hand side, south is on the right hand side. In the diagram, if they interchange, you have to be very careful, because we know whenever we are using left hand rule, first forefinger we are going to assign, that too in the direction of magnetic field, correct? So here the magnetic field is from north to south, always is from north to south. In this diagram it is from left to right. If the north is that side and south is on this side, then the direction of magnetic field be towards left. Okay, all these things you should analyze it properly once. Now we'll understand the parts. Listen, A, B, C, D is a armature. What do you mean by armature? Armature is very simple, a rotating part in a device. In any device, a rotating part is called as armature. That's it, very simple. So A, B, C, D is going to rotate, right? So it's an armature. That's it. Next, B1 and B2. See here, B1 and B2, these are the brushes. Actually, why do we need a brush? Just to give the connection from battery to the S1 and S2. We are going to learn what is S1 and S2, don't worry. What is the function of brush? Okay, just to give the connection from the power source to the split ring commutator. Split ring commutator. Now we'll learn more about these brushes. These brushes, what if there are no brushes? What if there are no brushes? There will be no connection between S1, okay, this line power source and split ring commutator. There will be no connection, so no current will flow. But according to the present technology, many motors are brushless. Brushless motors are efficient compared to these old motors. These are the old motors which are still, I don't know whether these are in our mixer grinder or fan, but definitely it is there in our textbook. Old, outdated topic. Okay, outdated topic. In many cases we are using these kind of motors, but technology has been improved, so they have removed these brushes. Without brushes also, now the present motors are running. Those are called as brushless DC motors. Okay, those are efficient. Okay, efficient, and they'll run faster compared to this one. But according to our textbook, brush is very much important, even though it is outdated. Now listen. So brush. Okay, brush. What is the function of brushes? We use the connectivity from the source to the split ring commutator. Now, what kind of brushes we are using? We are using carbon brush. Carbon brush. So many students will get doubt, because these kind of things will not be specified in the textbook. Why we have to use carbon? Why not other material? Very simple. If you use other material also, the connection will be there, but few things which few properties which carbon has, that properties will not be there in those material. What are those properties? First, it has a high conductivity rating. Connection is good. For when it comes to conductivity, we can use other materials also, but few things. When this, see, this is connected to S1, correct? So these split rings are going to rotate, so there will be a friction. So when we use carbon brush, the wear and tear is minimum. Wear and tear is minimum. That is one advantage of carbon brush. Then carbon brushes are self lubricating property. They have self lubricating property. We don't have to add lubricators. Okay, these are the extra two properties why we have to use carbon brushes only, not other brushes. All these information are not there in your textbook, just for a knowledge. Few students will definitely get doubt, why we have to use carbon, why not other things. Why I am teaching you all these things? Because this generation kids, they are next level. The way they ask questions in the classroom, those are next level. They are OP, okay, overpowered kids. Okay, now, so B1, B2 is done. Then S1, S2. Split ring commutator. See, these are splitted, correct? That's why it is normally the name is commutator. Now it is in the form of ring. It will be in the form of ring. That's why it is ring commutator or commutator. We have splitted it, right? Split ring commutator. That's it. So what is the function of commutator? That I am going to teach you when we are learning the working. Okay. Now S1 and S2, one thing you should know, they are going to rotate. That is enough for now. Next, armature we learnt, brushes, and why carbon, why not other material, we got to know, and what is the meaning of split ring commutator, but the working we are going to learn. Now listen. So See, first, whenever you don't see a dot, that means this is an open circuit, current will not flow. But when you see a dot, that means current starts flowing. When the current starts flowing, see, from brush and here, so here, when the current is in this direction, see, for this material, okay, this line, okay, this line, the current is towards left, correct? And this one, the here also, see, AD, in AD the current direction is towards left, and BC the current direction is towards right. But what is important, okay, when the force will be generated, we know when the current carrying conductor and a magnet are brought together, okay, brought near to each other, okay, force will be generated. But in one case force will not be generated. In which case? When the direction of magnetic field and the direction of current both are same, both are in the same direction, or when they are in parallel, when they are parallel to each other, no force will be generated. Now see, in AD the direction is like this, and the direction of magnetic field is towards here, in this direction, correct? Magnetic field direction is towards, because we know it is always flow from north to south. So these two are, even though these two are opposite, but they are parallel, correct? They are parallel. When they are parallel, no force will be generated, no force will be generated. So when it comes to AD, okay, no force will be generated. Now we'll talk about BC. This is AD, correct? Now we'll talk about BC. Okay, in BC, okay, here the direction of current is towards right, and when it comes to north and south, okay, magnet, the direction of magnet is also in the same direction. When the direction of magnetic field and the current are in same direction, when they have same direction, no force will be generated. There are two cases. So in the plane, this is the plane, this is called as, see, when it comes to a coil, this is a flat coil, correct? Flat coil, like a sheet of paper, correct? Whenever we talk about a flat coil, see, the top layer, this top line and the bottom line, these are called planes of the coil. These are called planes. So these are called what? Planes of the coil. This you should know. Now we'll talk about these lines, AB and CD. Now see, AB, first we'll talk about AB. If we know AB, that is enough. Why I am only seeing AB, why not CD? Okay, I'm going to use left hand rule in the direction of AB. I'm not going to use CD. Why? Because we have to use for the current direction which is near to the starting point of the magnetic field. This is the starting point of the magnetic field. It will start moving from north to south. So where is the north here? Which line of coil is near to that north pole? AB. So this direction of current we are going to use it in left hand rule. Now this is now it is the time to apply our Fleming's left hand rule. Okay, now first always assigning the forefinger. This is very much important. Forefinger. Why forefinger? It always represents the direction of magnetic field. See, first this is how we can easily say this is the direction of magnetic field, because it's starting from north to south. If north is this side, then you have to use it like this. Keep this in mind. If north was this side, you should not use it like this, because this is the starting point. This is the starting point. From here we have to use. If the north was that side, we have to use it like this, because the starting point of magnetic will be this side if north was here. Now we'll talk about how to hold it. Now see, first assignment is done. Assigning the direction of magnetic field line. Now see the direction of current. This middle finger represents direction of current, correct? But the direction of current is upward direction. This is towards me. Just rotate it. Just rotate it. See, now see. Now this forefinger represents the direction of magnetic field, and this middle finger represents direction of current. If these two are there, okay, this thumb represents, see, thumb is towards the board, okay, towards downward direction. See, downward direction. When the force is in downward direction, see, this coil can rotate in two ways. If the force is applied in upward direction, this is going to produce clockwise direction. See, if the force is upward direction, it is going to produce clockwise. If the force is downward direction, inward, okay, if the force is inward, then this is going to produce, see, if this is inward, this coil is going to, armature is going to rotate anti-clockwise direction. Now because of the Fleming's left hand rule, according to this one, the force is downward, correct? The force is downwards or towards the board, correct? That towards the board means inward only. Towards the board means inward. Okay, if it is towards the observer, that means outward. Keep this in mind. If something is away from, if the force is away from the observer, that means inward. Okay, if the force is towards the observer, if it is like this is outward. Now according to the direction, okay, of course it is towards the board, so it is inward. Inward means from top to bottom. If the top to bottom is there, so this is going to rotate like this. Okay, if the force is inward means top to bottom, like coming downward, so this is going to rotate in anti-clockwise direction. That's it. Now we got to know how to use Fleming's left hand rule in a DC motor. So first thing, what are the important thing? The functions of parts. Okay, now we have to talk about split ring. So working, the rotation, how it rotates, that is enough. The complete working is not required, that is not there in the syllabus. Whether it will rotate in clockwise or anti-clockwise, the first step is very much important, that we have learnt, okay, based on the direction of magnetic field and based on the direction of current. Now we'll talk about split ring commutator, why it is important. Now listen. Okay, assume this is the coil. Okay, initially this is A, B, C, D. Okay, A, B, C, D. Once the force is upward direction, it is going to rotate like this. It is going to rotate like this. Now, initially when it was like this, the current direction was like this, correct? The current direction was upward. But when you turn it, the current direction becomes downward. The current direction becomes downward. So what happens now? As the current direction is downward, okay, it will not continue to rotate. Initially it was up, right? It was up, so it made a half rotation. It made half rotation. Now for a present situation, the current direction is downward, so it will not complete that rotation. It will not complete that rotation. So this armature will be flipping like this. For every half rotation, it will be flipping like this. This will be happening inside a motor if there was no split ring commutator or commutator. So what is the function of commutator? So this commutator will change the direction of current. Will change the direction of current in an armature for every half rotation. After every half rotation, see, this is half rotation. So see, this is half rotation. So if it completes like this, that is one full rotation, correct? So if this is half rotation, for every half rotation, the direction of current in the armature will be changed by the commutator to make sure this armature it is rotating in one direction. So it will be rotating in one direction if we change the direction of current for every half rotation. That is the function of split ring commutator. Now we'll talk about an important topic when it comes to DC motor or AC generator, that is nothing but plane of coil. Plane of coil. So here this one, before understanding this one, we need to understand the basics. We know the basics. See, if current direction is perpendicular to direction of magnetic field. So current direction is perpendicular to direction of magnetic field, maximum force will be generated. If I is parallel, okay, if current direction, not current direction is same or parallel, no force will be generated. If current direction is same or parallel to direction of magnetic field, no force will be generated. This we know, correct? Whatever the concept we are going to learn now, this will be exactly opposite to this one. Okay, exactly opposite to this one. That's why I thought this one also. Now listen, plane of coil. So whenever we talk about coil, in this shape or rectangular shape, any shape is enough. First, visualization is very much important. Whenever we talk about plane of coil, this coil is flat. What is this? Flat, correct? See, it's like a piece of paper. Okay, this top end and the bottom line, this end, this bottom end and the top end is called as plane of coil. This part, see, this part and this part is plane of coil. When this plane of coil, I will write it as POC, plane of coil, is in same direction to magnetic field, maximum force will be generated, max force will be generated. See here, when current is in the same direction, or see, same or parallel, same direction or parallel, any one word they can use. If POC, plane of coil, this is in the same direction, see, now at the present situation, this is the plane of coil, correct? This is parallel to the direction of magnetic field, correct? This is parallel or in the same direction, any one word is same, okay? A plane of coil is in the same direction to the magnetic field, or plane of coil is parallel to the direction of magnetic field, then the maximum force will be generated. Compare this one here. When the current is same or parallel to the direction of magnetic field, no force will be generated, but here maximum force will be generated. So whenever the question comes to magnetic field is fixed, in both the questions magnetic field will be fixed, whether they are talking about direction of current or plane of coil, that is important. So these two are exactly opposite, okay? During the theory solving video also I have to explain this one. Now only you understand, then those kind of questions will be easy for you, you will understand immediately. Now when the same plane of coil is perpendicular to magnetic field, okay? So now see, it is like this, this is the plane of coil, correct? When it is like this, when it is the magnetic field, north side is this side, right? The magnetic field is like this, the plane of coil is like this. See the direction, perpendicular to each other, correct? When the plane of coil is perpendicular to magnetic field, no force will be generated, but here when it comes to current, direction of current and magnetic field, okay, maximum force will be generated when the direction of current is perpendicular to direction of magnetic field. Now we learn ways to increase the speed of rotation of the coil. We know the armature ABCD is the coil, right? How to increase the speed of that coil? There are 4 ways. First, increase the number of turns of the coil. We know that coil is wounded around a soft iron. The armature is soft iron. Around the soft iron, coil is wounded. Okay, now we got to know number of turns are there, correct? In our first part only we understood number of turns are directly proportional to increasing the strength of the magnetic field, correct? So this is one way. By increasing the number of turns of the coil, you can write like this, or by increasing the windings of the coil, you can write any one. Next, by increasing the current in the circuit, more current, more will be the force. If force is more, then the speed will be more. Then by increasing the strength of the magnet which we have used a magnet, correct, normal magnet. By increasing the strength, if we use stronger magnets, the force will be more the force, more the speed will be there. Then whatever the coil we have used, the coil, okay, the coil, if we increase, by increasing the area of the coil, the area is nothing but the thickness of the coil. More the thickness, okay, if the thickness is more, what happens to resistance? Resistance decreases, correct? Resistance decreases. If resistance decreases, current increases. If current increases, more speed will be there, more force, more speed, correct? So thickness of the coil, these are the 4 factors, okay? In the exam they may ask you any one, they are not going to ask you any 2, they will ask any one, or else they will pick one of these points, create one question based on that. So if you understand these things properly, without by hearting, understanding, if you understand it properly, any question you can answer it easily. and one small topic is left. What is the energy conversion in DC motor? What do you mean by energy conversion? Which form of energy is converted into which form? That is the meaning of this one. See here, a few things you need to know. What is the input we are giving? What is the output we are getting? That if we know that, we can aram se answer this kind of question. What is the energy conversion in DC motor? Okay, we are giving what? Electricity, electrical energy. So, and it is giving us rotation. What do you mean by rotation? Rotation is nothing but kinetic energy. Kinetic energy is a form of mechanical energy. So we are giving electricity and it is giving us mechanical energy. So electrical energy is getting converted into mechanical energy. This is the conversion in DC motor. So for now we have learned the complete concept of part B. Okay, now after this one immediately go for theory solution. There now you have only 50% of the knowledge. Based on the question you will get 30 to 40% of the knowledge. Remaining 10% is logical and application questions. Those questions you can only get the knowledge by solving previous year papers as well as the new upcoming latest logical and application questions. All these videos we have done, that too in chapter wise. So from the chapter electromagnetism, what are the logical and application questions? Only from that chapter. And also in previous year papers, what are the questions asked in only electromagnetism? We are not just going to give you the previous year paper like that and solution. Only from this chapter, only from all the particular chapters, chapter wise we are going to teach you the previous year papers as well as the logical and application questions. All those videos are available in the description box. So watch it, learn everything and get 80 on 80 without touching the textbook. Thank you.